I owe you exams. I'll get those back to you on Monday, for sure, on Monday. We talked about stresses in beams due to torque for solid circular cross sections. What's the other type of cross section that we can do?
Rectangular.
Yeah, well, any thin walled shape, but rectangular was the one where we could also do the shear force and the whatever. So now we're going to do closed, son of a, okay, closed thin walled tubes. How thin is thin enough? The long answer doesn't, there's no like clean answer for it really. It's just a matter of how much precision you need. But the short answer, let's say that 1/10 of the radius,
Of the radius?
Of the, yeah.
Yeah, like the distance from the centroid or whatever.
Right. Yeah. And yeah, that's for a circular shape. For other things, I mean, just think 1/10, and that's about that's already more detail than I really have, any support to give you. But let's think just 1/10 of the size of the cross section. And remember what closed means. We can't have, so this is okay, but this is not okay. So again, we're going to do the temporary coordinate system thing and use a rotation matrix at the end. So we're going to choose our temporary capital X, Y, Z coordinate system with the Z axis, the capital Z axis. An outward facing normal at the desired location. Okay, so for example, if you have a weird shape like this, and by the way, marvel at how amazing it is that we can calculate any kind of meaningful stresses in a wacky cross-sectional shape like that. But if you're interested in the stress over here, then our temporary coordinate system would be oriented like this. And if you're interested in a point over here, your temporary coordinate system would be like this. Okay. And in that temporary coordinate system, your capital X, capital Y stress, shear stress, is equal to the negative of the torque divided by 2 times the wall thickness at that point, because remember the wall can be, the wall thickness can change as you go around the outside. So 2 times the thickness times the median area, and I'll show you what all these mean. And like every other kind of stress that I've given you, you can trust the signs that you get out of this. So this lowercase t is the thickness of the wall at the desired location. And the median area is the area inside the median of the wall. All right, so what does this mean? So let me draw like a general. I'm drawing the wall a little thicker than it probably should be just to get this point across. But the median of the wall is just, think of it as where the stripe on the road would be. Okay, so that's the median. And then the median area is, forget about the fact that it's hollow or whatever, it's just the area inside this. I'm going to be cross-hatching this the rest of the day. For some complicated shapes, this can be sort of a mess to calculate. So notice, don't kill yourself getting an exact median area. Don't kill yourself to get the exact median area. The fact that this is thin-walled means that the outer area, go to the outer edge of the wall and take that area, is really not too different from the median area, is really not too different from the inner area, So there are a lot of cases where it's a lot easier than calculating that median area, is just calculate the outer, calculate the inner, and average them. It's not exact, but it's close enough, more than close enough. Where does that, it's hard to imagine, isn't it, what the physical meaning is of, how in the world, it's pretty common that you'd look at a simple formula like this and try to make sense out of the various parts. I just want to say that the area inside the median of the wall is totally a mathematical artifact of the derivation process. You'll never make sense out of that. It's just they went through, they did all this stuff, they came out with some terms that they're like, oh, if we lump this together, there's a nice, concise way to describe this lump of stuff, So, don't try to find any more meaning than that, really. One other thing to notice here is, like for a circular cross section, remember there was that rho value in the calculation. So, and the effect of that is that you're always going to have a bigger stress as you go closer towards the edge of the cross section. Okay. I'm going to erase this in a second, but this was the formula we did yesterday. And so as that row gets bigger, as you get closer to the edge, you're always, like, even if it's a small distance, any small distance out is increasing the stress.
That's for a solid round stock?
Yeah, that's right. Well, when we're dealing with thin-walled things, the assumption we're making is that the wall is thin enough that we're treating the stress like it's the same the whole way through the wall at that location. Okay, and so you see that none of this takes into account in any way where you are through the thickness of the wall. We're assuming it's the same. Yep.
Isn't it just, doesn't the equation just mean the thicker it is and the bigger it is, the harder it is to twist? What do you mean you should try to make sense of it?
Well, yeah, that's a great way to think about it. But I'm just saying, like, if you're going to try to figure out, so yeah, that's pretty reasonable. Yeah, I mean, if you think of like the
Yeah, I feel like there's no way you can
Yeah.
make something bigger without making it harder to twist.
Yeah.
Like if you like add like little
Right.
nodules to something, all
Right.
of a sudden it becomes like a spline. Or
Yeah.
like-
Yeah, you're totally right about that. But the fact that, like, why does this have to be the median of the wall? What does that have to, like, I'm just saying, like, this median of the wall thing to me looks pretty arbitrary. And then when you go into the derivation, it's like, oh, it really is just a bunch of stuff that they threw together. And then we're like, oh, there's an easy way to describe these if you throw them together in this particular way, you know.
So for like the sake of doing our problems and stuff, though, we should still try to calculate the median area.
Yeah, I mean, if it's a rectangular shape or a circular shape, you might as well. It's easy to do. But for like a triangular shape, even it gets pretty messy. I would just calculate the inner, calculate the outer, and average them. That's really the error that you get in your median area is much less than the area you're going to get from the assumptions they're making in the derivation and stuff like that. So now, there is one case where we can check the results against each other. So let's do that, and we're going to do it two different ways. And I'm just going to choose. I'm just going to choose some numbers, and we're going to just kind of get a sense of like how close these things are to each other. So if we have a hollow circular cross section, we can do these calculations two different ways. So let's compare. And we'll just do it for one case. Actually, my notes here, what I did last time was like all like symbolic, and let's not do that. Let's just pick out some numbers that are in the realm of what we might expect and just see how close they are. So let's say we have a thing like this. It doesn't matter how long it is. And let's say that we'll apply a torque to the left side this way of 500 Newton meters. And that's the only external load we're worried about. And for the cross section, let's say that the outer radius is, let's make that 5 centimeters. And then the inner radius, so a tenth would be, let's do it for a tenth. So let's say that this is 0.045,
Or 5.
right? And let's choose a point to calculate the stress. Just to keep getting used to rotation matrices and stuff, let's calculate it here and here. Okay. Well, if we're using the thin-walled assumption, what do we know about the stresses at those 2 points?
Equal.
They're equal, yeah. They're going to be the same. And so what we're going to get for when we use the circular cross-section approach is two values that are close to each other but not equal. Okay. So let's start with the circular approach. And I guess we might as well first do the internal loads. So the internal torque, just make sure we get this right. So there's only one cut. We have the 500 here, the internal torque here, the moment equation about the x-axis says 500 plus t is 0. So the internal torque everywhere along the length is negative 500. And now we'll use that for the circular approach. We're going to use a coordinate system, a temporary coordinate system with the z-axis pointing that way. That means the temporary y-axis points this way. And our tau xy is equal to negative of the negative 500 we just calculated times rho divided by I sub p. And that polar moment of inertia is pi over 2 times the radius outer to the fourth minus the inner radius to the fourth I'm never going to be healthy again. I've just come to accept it. I cry a lot though.
That's healthy.
Yeah, I think it makes me feel better.
Is it allergies?
I don't know. I've never had a winter like this before. It's like I don't even get fully healthy again before I start the next thing, you know?
I feel like the flu that went around this year was extra bad.
What the? How can you say that's not going to work? Oh, I see. Okay, so this is. Oh. Okay, now I have it. 3.376 times 10 to the minus 6. And this is meters to the fourth. And so at the outer point, tau x y is 500 times 0.05 divided by 3.376 times 10 to the minus 6. And that is 7.405 times 10 to the 6 pascals. And then at the inner part of that wall, tau x y is equal to 500 times, what's the row value here?
0.045.
Yeah, 0.045. And that is 6.66, oh no, times 10 to the 6 pascals. Devil stress. So, you know, it's noticeable, but all of this stuff, like if you've taken, say, circuits, you get this sense that engineering, you know, you have this ultra precision, you know, instrument to calculate this stuff. And in some areas of engineering, that's true, but in others, it's not really true. And mechanics of materials is one of those where a lot of times you're just trying to put sort of limits on things or whatever. Those are pretty noticeably far apart, although they tell kind of a similar story. You know what I mean? It's somewhere in the 7 times 10 to the 6th pascals area. When we do the thin-walled approach, we're just going to get something in between those two. Okay, which makes sense. And so for treating this like having thin walls, we're just going to basically say that the whole thickness of the wall has a stress of about 7 times 10 to the 6. And then we'll do the rotation matrices after we're done. So for this approach, we have that tau, capital X, capital Y, is equal to negative t over 2 times t, the thickness t, times the median area the median area we can calculate as, so the median area is at a radius of 0.0475. Everyone see that? So the area is pi times 0.0475 squared and so that is 0.007088. And so tau x y is equal to negative of negative 500 times 2 times point, the wall thickness was 0.005. If the wall thickness varies, remember to use the wall thickness at the spot that you're looking at. And then 0.007088. And you get 7.05 times 10 to the 6. Okay. Now, if there were other types of internal loads going on, you would have to, before you can add the stress tensors, you need them all to be in the same coordinate system. So now let's just do it the one time for the 7.05 times 10 to the 6, but let's express this in the coordinate system that we want to use. So we'd be going from this coordinate system to this coordinate system. And what kind of rotation is that?
90 degrees about x.
Positive 90 degrees about x. And so the rotation matrix is, so we got 1, 0, 0, and then zeros down the first column. Oh, this isn't interesting enough for you, David?
Oh, I'm sorry. No.
Okay. I don't like to see that kind of face in this class. What's the cosine of 90 degrees? 0. Sine of 90 degrees is 1. Okay, so negative 1, 0. Okay, so there's your Q matrix. And so our final stress tensor is Q times our starting stress tensor that we got in that temporary coordinate system times Q transpose. So that is Q times, I guess I never wrote this, but it's times 0, 7.05, I'll just do it in megapascals. 0, 7.05, 0, 0, 0, 0, 0, and then times Q transpose. That gives 0, 0, negative 7.05, 0, 0, 0, negative 7.05, 0, 0 megapascals. One thing that's really easy to do is forget to multiply by that second matrix transpose. There's an easy way to catch that. You almost never get a symmetric matrix out if you forget that. Okay, remember stress tensors always have to be symmetric matrices. So like in this case, if I had just gone, if I had just taken Q times that matrix and then got excited and hit enter, I would get 0, 7.50, 0, 0, 0, negative 7.0500. It's not a symmetric matrix. Okay. Anybody have any questions about that?
Is IP different from IA?
Yes. So the
Is there a different list of equations to know, or is it just the
well, you don't have to know them, but yeah, like those will both be given on an exam or something.
Okay.
But yeah, there's different formulas for them. The only one that we only use polar moment of inertia for one thing, for circular cross sections, and so you only need one formula, and the formula is what I gave you at the start of this problem, wherever it is.
R outer minus R inner to the fourth times pi over 2.
Right, but it's just remember it's R outer to the fourth minus R inner to the fourth, which
I have it written down like that.
okay, yeah, it's not quite the same as
No, I'm aware. I just said it like
Okay.
that at the same time.
yeah. All right, well, let's just stop there, and we'll do a couple examples next time of like full problems, with every kind of thing thrown at you. But if I want to give you a problem that has everything thrown at you in one single problem, so if there's bending moment, shear force, tension, torque, there are two options for cross sections, or two options for where I can ask this stuff. That is a circular cross section, but then I can only ask you stuff that happens along the neutral axis because of shear force. And in that case, I can't make you do any calculations involving bending moment because the stress due to bending moment is 0 along the neutral axis. Or the only place where you have to do every kind of calculation is for a rectangular cross section with thin walls. A rectangular thin walled tube. Yeah, I guess.
Taller than it is wide?
Taller than it is wide, correct. Yep, exactly. Okay, that's all. Goodbye.